Sirens cut through the air, but they arrive too late. Smoke is already layering the ceiling, turning every breath into a calculation. Visibility collapses first, then decision-making, then time. In confined spaces, fire does not kill by flame alone, it kills by physics. Heat stratifies, oxygen depletes, toxic gases accumulate, and human reaction time shrinks to seconds. In that compressed window, one object sits quietly on the wall, ignored in daily life, assumed to have a single purpose. But the engineering inside a standard fire extinguisher is not just about suppressing combustion. It is a pressurized system, a chemical dispersal device, a thermal control tool, and a kinetic instrument. 4 distinct mechanisms, each governed by measurable science, each capable of altering survival outcomes when conventional assumptions fail.
Most people are trained to think of a fire extinguisher as binary. Pull the pin, aim at the base of the fire, squeeze, sweep. That simplified instruction is correct for basic suppression, but it hides the deeper reality. A fire extinguisher is fundamentally a sealed pressure vessel. Inside, compressed gas stores potential energy. The extinguishing agent acts as a particulate or chemical medium, and the nozzle converts stored pressure into directed flow. This combination creates effects beyond extinguishment: displacement of oxygen, rapid cooling through expansion, particulate obscuration, and short-duration thrust. These are not improvised interpretations. They're direct consequences of thermodynamics, fluid mechanics, and combustion chemistry. Understanding those consequences changes how the device can be used when conditions move beyond textbook fires and into survival scenarios.
The first misunderstanding begins with pressure. People assume the extinguisher simply sprays material. In reality, the device contains gas, often pressurized between 10 and 20 bar, depending on type. When the valve opens, that pressure equalizes violently with the surrounding environment. Gas expands, velocity increases, and the stream exits the nozzle at speeds that can exceed 20 meters per second. That means the extinguisher is not just dispersing powder or foam. It is generating a directed jet capable of moving air, smoke, and even small burning debris. The hidden science here is momentum transfer. When a high-speed stream exits the nozzle, it entrains surrounding air, pulling it into motion. This creates localized airflow in environments where ventilation may otherwise be non-existent. In smoke-filled rooms, this temporary airflow can push toxic gases away from the breathing zone for seconds that matter. Evidence for this effect appears in industrial safety studies where extinguishers are used to clear sensor obscuration. The same fluid dynamics apply in survival conditions. The implication is subtle but critical. Even when flames are not immediately suppressible, the extinguisher can create a brief corridor of breathable air, buying time for orientation and escape.
Escalation begins when heat enters the equation. Fire environments produce thermal layering, with temperatures near ceilings reaching lethal levels, while lower air remains survivable. The second weapon, hidden inside the extinguisher, emerges from expansion cooling. Many extinguishers, especially CO2 types, rely on compressed carbon dioxide stored as liquid. When released, it undergoes rapid phase change and expansion, absorbing heat in the process. This is the Joule-Thomson effect in action. The discharge plume becomes extremely cold, sometimes forming dry ice particles. Misunderstanding this leads people to treat the extinguisher only as flame suppression, but the hidden capability is localized cooling. Surfaces too hot to touch can be cooled temporarily, metal door handles can be tested safely, and small ignition sources can be reduced below combustion temperature. Thermal imaging studies in firefighting training show temperature drops of dozens of degrees Celsius in targeted zones. The survival implication is direct. Cooling a handle before opening a door reduces the chance of flashover exposure, and lowering surface temperature can prevent burns during escape. But cooling alone is not the full story. The third mechanism involves chemistry. Dry chemical extinguishers typically contain monoammonium phosphate or sodium bicarbonate. These powders do not simply smother flames, they interrupt the chemical chain reaction of combustion. Fire sustains itself through free radicals, highly reactive molecular fragments. When the powder disperses, it interferes with those radicals, halting propagation even when oxygen remains present. The misunderstanding is assuming that once sprayed, the agent's usefulness ends. In reality, the dispersed powder lingers in the air, creating a temporary fire-resistant environment. Studies in fire dynamics labs demonstrate reduced reignition rates in spaces saturated with dry chemical agents. This lingering cloud acts as a buffer, slowing flame spread. In survival terms, that means a corridor sprayed moments earlier may resist reignition long enough for passage, even if the primary fuel source still exists nearby. The extinguisher becomes not just a suppression tool, but a transient protective barrier.
The fourth weapon is the least obvious and often ignored because it is mechanical rather than chemical. When the extinguisher discharges, Newton's third law applies. The expelled mass produces a reactive force. While not strong enough to propel a person significantly, it can influence balance, push lightweight obstacles, or break fragile barriers when used at close range. Emergency testing has shown that directed discharge can scatter burning papers, push aside hanging fabrics, and disrupt small flame fronts by sheer kinetic energy. The misunderstanding is dismissing the extinguisher as passive. The hidden science reveals it as an active directional force. In confined spaces, even slight movement of burning material can prevent flame bridging across escape routes. The implication is not brute force, but controlled repositioning, altering the geometry of the hazard long enough to move through it.
Each mechanism compounds the others. Pressure creates airflow, expansion cools surfaces, powder interrupts chemistry, and discharge provides directional force. Together, they form a layered survival system hidden in plain sight. Most environments containing extinguishers, offices, vehicles, corridors, are also environments where evacuation routes can become compromised. The escalation occurs when conventional escape paths fail, and seconds determine outcomes. At that moment, understanding the engineering inside the extinguisher transforms it from a single-use device into a multi-purpose survival instrument. The transition is subtle but profound. Instead of asking whether the fire can be put out, the question becomes how the device can manipulate air, temperature, chemistry, and movement to create an exit where none appears to exist.
And the deeper reality emerges when smoke density increases. Visibility drops below 1 meter, and the human brain begins to lose spatial awareness. In those conditions, the first weapon, directed airflow, interacts with the third, chemical dispersion, forming a temporary navigational marker. The plume becomes both breathable corridor and visual contrast against dark smoke. Evidence from evacuation drills in zero-visibility chambers shows participants orienting along discharge paths more effectively than unaided movement. The extinguisher is no longer just countering fire, it is countering disorientation. The survival implication expands beyond physics into cognition. When panic rises, structured action, pull, aim, discharge, anchors behavior, reducing hesitation. But this is only the surface of what the device can do when analyzed through engineering rather than assumption. Because the moment heat intensifies further and structural materials begin to fail, the interaction between pressure vessel design and human reaction time introduces a new risk and a new opportunity.
The temperature climbs beyond the point where plastics soften and structural adhesives begin to fail, and the environment transitions from hazardous to actively unstable. In this stage, the fire extinguisher's role shifts again, not because its components change, but because the surrounding physics do. A pressurized cylinder exposed to heat becomes a measurable variable in the thermal equation. Inside the vessel, gas pressure rises as temperature increases according to the ideal gas relationship. Even extinguishers designed with safety margins can vent or rupture if overheated. This is usually framed only as a danger, but the analytical reality is more nuanced. The misunderstanding is believing the extinguisher must be kept distant from heat at all times. The hidden science shows that controlled placement and discharge timing can exploit pressure behavior without risking structural failure. By discharging earlier, the internal pressure drops, reducing the risk of cylinder compromise while still using stored energy to influence the environment. Evidence from fire safety engineering demonstrates that partially discharged extinguishers exposed to heat are significantly less likely to rupture because internal pressure is reduced. The survival implication becomes counterintuitive. Using the extinguisher sooner, even before flames are directly in front of you, can reduce both environmental heat and the device's own hazard profile.
This introduces the second layer of escalation, time-dependent efficiency. The extinguisher is most powerful in the first seconds of discharge, when pressure is highest and the plume is most coherent. As the contents empty, flow weakens and particle density drops. People often conserve the extinguisher, releasing short bursts only when flames appear directly in their path. That instinct seems logical, but fluid dynamics suggest a different strategy. A continuous, controlled sweep creates a stable cloud, maintaining a temporary microenvironment of reduced temperature and suppressed combustion. The misunderstanding is equating conservation with effectiveness. The hidden principle is saturation. Combustion relies on continuous chemical reactions. Interrupting those reactions across a wider area for a shorter duration often yields better survival outcomes than intermittent bursts. Fire testing in enclosed compartments shows that sustained discharge lowers overall flame intensity more effectively than multiple short pulses. The implication is strategic. The extinguisher should shape the environment, not just target individual flames.
Smoke toxicity introduces another dimension. Most fatal fire incidents involve inhalation of gases such as carbon monoxide and hydrogen cyanide. These gases disperse unevenly, forming pockets of lethal concentration. When the extinguisher discharges, the turbulent plume mixes layers of air, diluting localized concentrations. This mixing effect is not widely discussed because extinguishers are not designed as ventilation tools, yet the fluid mechanics remain valid. The misunderstanding is assuming the extinguisher only affects visible fire. The hidden science is turbulent diffusion. When a high-velocity jet enters a stagnant environment, it increases mixing efficiency, reducing gradients of toxic gases. Experimental smoke chambers demonstrate that forced mixing can lower peak concentrations in the breathing zone, even if overall air quality remains poor. The survival implication is limited but meaningful. A few seconds of reduced toxin concentration can extend consciousness long enough to reach an exit.
As conditions deteriorate further, visibility collapses completely and spatial orientation becomes unreliable. In zero visibility scenarios, people often move upward or toward perceived light sources, which may lead deeper into danger. The extinguisher's discharge provides tactile feedback through recoil and audible noise. These cues become navigational references when visual information disappears. The misunderstanding is thinking navigation depends solely on sight. The hidden principle is multisensory orientation. Humans can follow airflow direction and sound gradients even in darkness. When the extinguisher is directed toward a suspected exit, the plume's flow and sound reflect off surfaces, subtly indicating boundaries. Firefighter training exercises confirm that airflow patterns can help identify doorways or open corridors. The implication is behavioral. The extinguisher becomes not just a defensive tool, but a probing instrument, revealing structure through physics.
The chemical component introduces another overlooked factor: residue adhesion. Dry chemical powders cling to surfaces, especially heated materials. This coating reduces surface ignition potential temporarily.
The misunderstanding is viewing the powder as a transient cloud only. The hidden science involves thermal insulation and radical suppression at the surface level. When powder settles on fabric, wood, or paper, it creates a thin barrier that delays reignition. Laboratory burn tests show treated materials taking longer to reignite compared to untreated controls. The survival implication is sequential protection. By sweeping the discharge ahead of movement, surfaces that might ignite during escape are temporarily stabilized. This is not permanent suppression, but it stretches the time window for passage. The escalation intensifies when structural components begin to emit radiant heat. Radiant heat travels in straight lines, raising temperatures even without direct flame contact. Here, the extinguisher's plume acts as a particulate curtain. Suspended particles scatter infrared radiation, slightly reducing heat transfer. This effect is small but measurable. The misunderstanding is assuming radiant heat cannot be influenced without solid barriers. The hidden principle is scattering. Smoke already reduces visibility through scattering. Dry chemical particles extend that effect into thermal wavelengths. Fire science literature notes that dense particulate clouds can reduce radiant heat flux marginally. The survival implication is subtle but crucial. Even a small reduction in heat exposure can prevent pain-induced hesitation, allowing continued movement. At this stage, the extinguisher's four mechanisms, pressure airflow, expansion cooling, chemical interruption, and kinetic displacement, are interacting simultaneously. The device is shaping air composition, temperature gradients, combustion chemistry, and physical layout. Yet one more factor emerges when analyzing the nozzle design itself. The nozzle restricts flow to maintain velocity, and that velocity creates directional control. By sweeping low, the plume pushes smoke upward. By aiming high, it can clear a line of sight. The misunderstanding is thinking the aim only matters for targeting flames. The hidden science is vector control. Changing the angle changes airflow patterns. Evidence from smoke control experiments shows that directional jets can temporarily redirect smoke layers. The survival implication becomes tactical. Aiming low while moving forward can preserve a thin, breathable layer near the floor.
The transition toward the next escalation occurs when the extinguisher approaches depletion. Pressure drops, plume weakens, and the environment begins to reclaim dominance. At this point, the device's remaining value shifts again, from active manipulation to residual effects. Powder coating remains, cooled surfaces retain lower temperatures briefly, and displaced smoke takes time to resettle. The misunderstanding is believing the extinguisher becomes useless once empty. The hidden principle is persistence. The environment does not instantly revert. The changes introduced linger for seconds that still matter. In survival scenarios, those seconds often define success or failure.
And when the final hiss fades and only the empty cylinder remains in hand, the situation seems to have reached its limit. But the engineering inside the extinguisher has not finished influencing survival outcomes, because even an empty pressure vessel, stripped of its contents, still embodies mass, shape, and mechanical strength, properties that introduce a final, often overlooked dimension of utility as conditions approach their most dangerous threshold.